Hello guys, this presentation or problems will cover several topics in physics and there is no particular order to it. Hope you will learn something as you try to answer them on your own. When a pendulum swings back and forth, what factor primarily determines its period is the time it takes for one complete cycle. Letter A, mass of the pendulum bob. Letter B, length of the pendulum. Letter C, amplitude of the swing. And letter D, material of the string. The answer is: as a pendulum swings back and forth, the expression for the period or the time it takes for one complete cycle or rotation can be shown A here in the equation, where f is the frequency or the amount on how many times it cycles back and forth, the angular velocity, the L or length of pendulum, and g the gravitational acceleration. Here we see that the period is proportional to the length L, A, so that means it primarily determines the period for that expression of the period. A, the shorter the length L, the shorter the period, and we see it in the simulation. A shorter period makes one complete cycle faster to achieve. Which of the following conditions must be met for two objects to have the same velocity after the collision? Letter A, the objects have different masses. Letter B, the collision is perfectly inelastic. Letter C, the collision is perfectly elastic. And letter D, the objects have different initial velocities. The answer is: here we have the inelastic collision, and it is where they collide but they move with the same speed and move in the same direction. In this case their momentum is the only parameter that is conserved. As observed, both masses move in the same magnitude and direction. This behavior occurs for inelastic collisions which the problem is asking. The other collision is elastic type, which is opposite to this, and you can learn more about them at the link provided. The equation of continuity for fluid flow can be derived from the conservation of: letter A, energy. Letter B, mass. Letter C, volume. And letter D, pressure. The answer is: an example of fluid flowing at a flow rate of 5,000 liters per second. The pipe has a regular cylindrical shape and particles flow at constant speed. At both ends the flow rate remains the same. The amount of mass entering and leaving remains the same. The amount of mass would be conserved. The pipe has an irregular shape. The diameter at certain sections is altered and the speed of the particles changes. The flow rate remains the same at these different points. The amount of particles coming and going out will still be the same. This suggests conservation of its mass, which allows us to directly obtain the relationship with the continuity equation as shown here. The continuity equation is showing the relationship of the cross-sectional area and speed at both ends. As the cross-sectional area changes, the speed also changes, but keeping constant the flow rate. Now to see the relationship of conservation of energy and fluid flow, we examine a Bernoulli's principle. To determine if there is a relationship between the fluid concept of continuity and conservation of energy, we look at the Bernoulli's principle. The principle states that the work done on a unit volume of fluid by the surrounding fluid is equal to the sum of the changes in kinetic and potential energies per unit volume that occur during the flow. In the scenario shown, the endpoints are also at different elevation, thus we take into account changes in potential energy due to gravity. As we recall, the total mechanical energy where kinetic and potential energies are the only present, then the mechanical energy at all points remain the same due to the conservation of energy. Thus, indirectly we can obtain the relationship of the continuity equation and conservation of energy. According to the principle of least action, What path does a system follow in order to minimize the action integral? Letter A, the path that minimizes the kinetic energy of the system. Letter B, the path that minimizes the potential energy of the system. Letter C, the path that satisfies Hamilton's equations of motion. And letter D, the path that minimizes the action integral itself. The answer is imagine you want to travel from one point to another, and you have various possible routes to take. The principle of least action is like saying that the actual path you will follow is the one that takes the least effort, as if nature is somehow efficient in choosing the way. In more technical terms, the action, or action integral, is a quantity in physics that represents a measure of how things evolve over time. It combines information about the energy of a system and how that energy changes. The principle of least action suggests that the natural path that a system takes between 2 points is the one for which this action is minimized. Water enters the inlet pipe with an inside diameter of 2.0 centimeters and flow speed of 2.0 meter per seconds. The other end of the pipe has a diameter of 1 centimeter. What is the speed of flow of water on the other end? Letter A, 8 meter per seconds. Letter B, 4 meters a per second. Letter C, 2 meter per second. And letter D, 1 meter per seconds. The answer is here we look at the image where a fluid enters a tube on one side with a diameter of 2 centimeters. The initial speed at this point is given as 2 meter per seconds. The water here is assumed to be incompressible with the flow speeds given by the continuity equation. Since it is assumed to be incompressible, the density cancels out and we are left with a much simpler equation. The area here is just the cross-sectional area. Substituting the known values, the diameters at both ends and the initial velocity, we are able to determine the velocity at the smaller diameter. This is shown to be 8 meter per second. It appears to be faster and in fact 4 times faster. This is a consequence of the continuity equation, which is in effect the conservation of mass. In a conductor, what happens to the electric field when the conductor is in electrostatic equilibrium? Letter A, it becomes zero everywhere inside the conductor. Letter B, it points in the direction of the current. Letter C, it remains constant throughout the conductor. And letter D, it is directly proportional to the voltage. The answer is when a conductor is in electrostatic equilibrium, any excess charge on the conductor will redistribute itself on the surface in such a manner that the electric field inside the conductor becomes zero. This redistribution of charges ensures that there is no net movement of charge within the conductor, and as a result, the electric field inside the conductor is zero. The displacement of one-dimensional simple harmonic oscillator of mass 100 grams is given by the equation shown here, which is a cosine function, where y is in meters and t is in seconds. The maximum kinetic energy is given as letter A, 0.5 joules. Letter B, it is 0.1 joules. Letter C, it is 10.8 joules. And letter D, it is 0.2 joules. The answer is if we draw the function, we see that it appears to behave like a wave. The 4 meter in the equation would be the amplitude or the highest value that the function can achieve. This is also called the maximum displacement. The time for one complete cycle would be called a period. This function is assumed to propagate over time, thus having motion. So, we look at the kinetic energy equation in relation to wave propagation. So, from the equation we see that the amplitude is given by 4 meters and the angular velocity is 0.5 radians per seconds. For maximum kinetic energy for a simple harmonic motion, the equation is given here. The details of the derivation of the formulation, you can refer to the link provided. So, if we substitute the given values to the equation, we obtain the maximum kinetic energy to be 0.2 joules. What is the name of the fundamental equation that relates electric and magnetic fields to the velocity of charged particles in classical electrodynamics? A. Letter A, Maxwell's equations. Letter B, Coulomb's law. A. Letter C, Lorentz force law. And letter D, Biot-Savart law. The answer is here we have a conducting wire with charges inside. The wire is subjected to an external magnetic field as shown here. The magnetic field induces a magnetic force onto the charge which pushes the charge upwards. The magnetic force that is pointed upwards is calculated by equation 1. Where Qi is the charge, V is the speed of the charge and B is the magnetic field. Reorienting the rod in a two-dimensional view. We see that the external magnetic field is going into the plane as indicated by the X mark. The magnetic force is still pointed upward the wire. Over time there will be an accumulation of positive charge particles at one end. Note that the conductor started as neutral or having equal positive and negative charges. Since the positive charges are migrating upward, the negative charges will migrate in the opposing direction. The separation of the positive and negative charges produces an induced electric field. The positive charge particle will experience an electric force due to the separation of charges creating an induced electric field, and it is given by the equation 2 shown here. The sum of the forces exerted by both magnetic and the induced electric field is called the Lorentz force, and it is given as equation 3. At what temperature are Fahrenheit and Celsius the same? Letter A, 40 Fahrenheit. Letter B, a negative 40 Fahrenheit. Letter C, 32 Fahrenheit. And letter D, negative 32 Fahrenheit. The answer is the equation that relates Fahrenheit and Celsius is given by equation 1. If the Fahrenheit and Celsius temperature are equal, then we rewrite equation 1 as shown here. We obtain a value of negative 40 Fahrenheit for the scenario to occur. When an ideal gas is isothermally expanded, which of the following is true? A. Letter A, the internal energy of the gas remains constant. Letter B, the temperature of the gas increases. Letter C, the pressure of the gas remains constant. And letter D, the volume of the gas decreases. The answer is here we have gas molecules being compressed by the piston. Although heat is added, the temperature remains constant. This case is called an isothermal process. For an isothermal process, the temperature remains constant as it expands or contracts. The internal energy delta U depends only on the temperature, but since this is constant, then its internal energy is zero. Here the heat Q is equal to the work output as shown in equation 1 of the first law of thermodynamics. The work for an isothermal process is equal to the number of moles times the gas constant R times the inverse a logarithmic function of the ratio of the volume as shown in equation 2. So, we can say that since the internal energy will be zero for the isothermal process, then it is constant. The end for now. For questions and comments you may send them to diyslearningstuff@gmail.com. You may review the slide on YouTube at Dies Learning Stuff. Thank you for watching and see you in part C.